Okay. This is the video, asynchronous video. I think I mentioned that previously that we're going to try asynchronous lecture in Zoom for a couple of times. So I'm going to record this video, and you have to watch this, and there will be a attendance for those who watch this video. If you don't watch it, then it's going to be marked absent. So we'll talk about that in a little bit more detail in the classroom, but this is just going to be a Zoom recording for concavity and the second derivative test. Okay, so let's take a look. So the concavity, definition of concavity is simply the concavity is that when you look at the graph or the curve, that which way is opening. Is it opening upward or is it opening downward? That's what the concavity is. But in terms of derivative, it has a little bit more to that idea. So we're going to put a little bit more definition to the concavity. So let f be differentiable on an open interval. The graph f is concave up if the f prime is increasing on an interval, and the concave downward if the f prime is a decrease. So if you look at the graph over here, and as you can see that, as you can see that, these slope of a tangent line is kind of increasing, so we know that it's going to be upward. On the other hand, if it's going to be decreasing, remember that this is decreasing now, so the tangent line is decreasing, then it's going to be concave downward. So when we talked about the increasing and decreasing functions, and the way we determined that was to find the f prime of x, and then use that function to determine an interval using critical numbers, and find out which part of the graph is increasing and decreasing. And from there, we can also find the relative extrema, and that was what we call first derivative test. So in order to understand the concavity, we're going to have to understand similar concept from the increasing and decreasing functions. The concavity simply, tells us the opening of the graph, but it works kind of similar way, where the interval is going to be, concave up or concave down, just like what we did in the increasing and decreasing function. So what we have now is that, we're going to go through the similar process that, we went through when you had the increasing and decreasing. So a test for the concavity is simply that if the let the f be a function whose second derivative exists an open interval. Okay, call it I. So if double prime of x, that's the second derivative, is greater than 0, then it's concave up. And if f double prime of x is going to be less than 0, then we know that it's going to be concave down. That's going to be testing for the concavity there. Now, just like we had a critical numbers for the increasing and decreasing function, we have something called points of inflections on concavity. So the points of inflection is that if the tangent line to a graph exists at a point at which concavity changes, then the point is a point of inflection. So the point of inflections tells us that the point that a curve changing their concavity, for example, from up to down or down to up. So from that point, that point of inflections, the concavities, start changing, from up to down or down to up. So point of inflection is going to be simply telling that, okay, now the concavity changes. Okay? Now, just like the first derivative test, we have something called the second derivative test. And what it means here is that, when we look at the first derivative test, and then once we filled it all the tables, and then we find out where the function is increasing and decreasing, and also give you the arrow that going up and down. So from that, if your arrow is going up and down, you know that that's going to be relative maximum. If the your arrow is going to go down and up, and that's going to be what the relative minimum is. Okay, we got a similar, similar test like that. Okay, so instead of using the first derivative test, you can use the second derivative test. If that's what you want to do. So if double prime of a c, if you take the second derivative is greater than 0, then at that point it's going to be relative minimum. So now the way we are going to find the relative minimum and maximum is that we don't have to look at the arrows going up and down. We're just going to have to look at the f double prime of a c. If it's going to be greater than 0, then it's going to be minimum. It's going to be less than 0, then it's going to be the maximum. So it's going to be a little bit better than, just, go through the entire table and then, look at the arrows going up and down or down and up. And instead, you can just look at the f double prime of c. If it's going to be greater than 0, then it's going to be relative minimum. It's going to be less than 0, then it's going to be relative maximum. However, if that f double prime over c is going to be equal to 0, then this second derivative test fails, and we don't know what's going on. So that means that you're going to have to go back to the first derivative test and find out, what is going to be a minimum or maximum. So that's going to be one drawback there. So we don't know if you want to use a second derivative test, and you took the second derivative and it's equal to 0, then you don't have a choice. You're going to have to go back to the first derivative test here. So the whole thing about the concavity here is that we're going to go through the similar process as we did for the increasing and decreasing of the functions. Instead, rather than looking at the functions decreasing or increasing, we're going to look at the concavities, whether the graph is going to be opening upward or downward, and that's going to be the one to. So let's just look at some couple of maybe 3 examples I'm going to give you. So let's say we have a function f of x equals to 6 of x squared plus 3. So we want to discuss the concavity. Okay. So a concavity simply means that you're going to have to come up with a second derivative. Okay. So let's just go through this. So first, I'm going to rewrite this. I am going to rewrite this as like this. 6 times x squared plus 3 to the negative 1. So let's find the first derivative. So that means we have what, 6 times minus 1 chain rule, right? X squared plus 3 to the minus 2. Now inside we have what, 2x. Okay. Why don't we simplify this one here? So we have what? 2x times minus 1 times 6, we get minus 12x on the top. And if I rewrite the x squared plus 3 to the negative 2, we get x squared plus 3 to the square. Okay. Now, since we are discussing concavity, we need to come up with the second derivative. Okay, there you go. We're going to have to apply the quotient rule here. So the bottom one, I'm going to call this one g of x. And top one, we're going to call this f of x. Right? I should have called this. This is a different f of x. Yeah, not this guy here. Maybe I should use this one. Let's just call the, I'm going to call this p of x. So we're just going to, follow the rules of a quotient. And so that means the g of x. Okay, so what do we have? Yeah, g of x means I have what? X squared plus 3 to the square times p prime of x. So derivative of minus 12x, we get minus 12. Let me write this here. So this is going to be g of x. This is going to be a p prime of x. Okay? Minus p of x. Minus 12x. Okay, so that's going to be your p of x. Then times the g prime of x. Now you're going to apply the chain rule here. So 2 times x squared plus 3. And exponent 2 minus 1 is 1. I'm not going to write that. So you're going to get 1 over here. And inside you get 2x. Okay, and that's going to be your g prime of x. And then everything has going to be divided by g of x squared. That means x squared plus 3 squared to the square. So here we don't have any choice. We're going to have to simplify these guys here. And we're going to have to find out what the x value will be. I mean, remember that, just like the, when you try to find the critical numbers, we are looking for the, make the function equal to 0, or the find the x value that makes function undefined. So, same thing here on when you try to find the inflection point of inflection here. So the entire process that we try to did over here, we are trying to find the point of inflection. So maybe I should write that here. So we're going to here from this guy f double prime here, we are finding points of inflections. So we're going to have to, make this thing equal to 0. That's one way. Or you're going to have to find the what the x value that makes this function undefined. Okay. So let's try this. So on the top, let's just simplify a little bit over here. I have a minus 12 x squared plus 3 to the square. I kind of wrote the minus 12. Right? And then let's just take a look at this one over here. I'm going to write this one. So the bracket over here, if I multiply these two, I get minus 24x squared. Okay, so these two, 2x times minus 12, you get minus 24x squared. Then you're going to have to multiply that. I mean, you could have done that with the 2 times 2x. That's going to be a 4x. Just do that. Right? 2 times 2x, you got 4x. So then you're going to multiply 4x times minus 12x. And that will give us what? Minus 48x squared. Right? Is it? Yes. So I'm going to rewrite this one over here. So I have minus bracket. So 2x times 2 times minus 12x, I have a minus 48x squared. Then I have x squared plus 3. Then at the bottom over here, I have x squared plus 3 to the 4th. Okay, so that's okay so far. Now let's rewrite this so I can eliminate the bracket over there. So I got minus 12, and I have x squared plus 3 to the square. And I have a plus 48x squared, and I have x squared plus 3. And divided by x squared plus 3 to the 4. Now let's look at the numerator up here. So if you look at the these two terms over here, okay, this one and that one. So if you look at the these two, we can take out the what would that be? X squared plus 3. Let's just take that out first. I have x squared plus 3. If I take that out, the first one, I'm going to have a minus 12 and x plus 3. And then on the other one, I'm just going to get my plus 48x squared. And the bottom here, we have what? X squared plus 3 to the 4. So as you can see, that some of these things are, getting more complicated here. So I made a mistake somewhere because that 2x over here minus 12. No, I think I'm okay. Let me see. I'm just going to make sure that I differentiate this one correctly. Okay, that's fine. Oh yeah, we're fine. Okay. So if you look at the outside here, you can cancel out the x squared plus 3 here, and that becomes a 3. Let me just rewrite this one more time. So what I have here is the I have a minus 12. Okay. Did I mess up here somewhere? That should be x squared. Sorry about that. Okay. So that means I have a minus 12 x squared plus 3 plus 48x squared and divided by x squared plus 3 to the cube. I'm going to simplify the top. So I'm going to multiply these out. find out what we have here. So you got minus 12 x squared minus 36 plus 48x squared divided by x squared plus 3 to the cube. So we can combine these x squared term over here. Okay, so that would be 36x. Then you have minus 36 divided by x squared plus 3 to the cube. And if I just take out the 36 from the front, then I'm going to have x squared minus 1 over x squared plus 3 and to the cube. So that's going to be our second derivative of the given function there. So in order to find the points of inflections, we're going to have to make that equal to 0 or find the x value that makes this function undefined. But fortunately, that if you look at the x at the bottom, that's going to be square. So you are not going to get anything subtract 3 that would make this function undefined. So this function doesn't have any x value that makes this function undefined because of the square there. So the points of inflections that we're going to get is simply f double prime is equal to 0. Okay. So we're going to make this function that f double prime that we got. We got 36 x squared minus 1 divided by x squared plus 3 to the cube equal to 0. So now if you multiply the both sides by x squared plus 3 to the cube, okay, then what you're going to end up here is going to be 36 times x squared minus 1 equal to 0. Because if you multiply, x squared plus 3 to the cube to 0, you get 0 anyway. And this one on the left-hand side, you can just cancel those out. Now, we're going to divide the 36 on both sides. All right. So then what you're going to get here is going to be simply x squared minus 1 equal to 0. So that means x square equals to 1, and x has to be plus minus 1. So that's going to be our point of inflection. Now, what does that mean? This is going to be the points that your concavity will change. Okay, so this is the points of inflection. Okay, so what we're going to do now here is just like the increasing and decreasing function problem. We are going to set up the table and find out where these concavities are changing. All right, so the interval and test value and the sign of f double prime. Okay. Okay, so we have an interval. Then we have a test value. Then we have a sign of f double prime of x. So if you go back to the increasing and decreasing function, it was f prime of x, right? Now we are talking about concavity, so it's f double prime. So we have a conclusion. So since we have the points of inflection is plus minus 1, we can set up the interval from minus infinity to negative 1, and from negative 1 to positive 1, and we can say from 1 to positive infinity. Okay? So I'm going to choose the test value for this interval, x equals to minus 2. Here I'm going to choose 0. And here we're going to choose x equals to 2. So plug that in value to the f double prime of function. So f double prime of negative 2 is a positive. And the f double prime of 0 is a negative. And the f double prime over 2, which is greater than 0, is going to be positive. So the conclusion here is that on the, sorry. So on the, then, if you go back to the, definition of concave up and the concave down, if the double prime of x is greater than 0, we know that that's going to be concave up. So here we're going to say concave upward. Here, concave downward. And here again, the concave upward. Okay. So now we know if you draw this picture here. Component. This is going to be a sketch of this graph over here that we are given. Okay. So the x equals to minus 1, and here x equals to 1. This is where the concavity changes. Okay. So over here and over there. So up to this point here, up to this point, the x equals minus 1 inflection point. Okay. If you look at the graph, it's opening upward. So this is why we have a concave up. And then from the x equals minus 1 to the x equals 1, you can see that the concavity is kind of going opening downward. So that's why you see a concave down. Okay. Then from here, the x equals 1, okay, and the gravity start opening upward. So that's why you see a concave. Okay. So the this function that I just drew is the original function that we have, which is f of x equals to 6 over x squared plus 3. So as you can see that this function is kind of continuous, and you don't see any x value that will give you this function undefined. There's no substitute. Okay, so that's why you see that concave up and concave down by looking at the f double prime over c. When you look at the inflection points, okay, so let me just write this down here for you. So here, okay. So this is going to be the inflection point points of inflection. Okay. So when we finish the analysis here, if possible, that you can draw the graph of the given function, you can kind of visually see what's happening in terms of a concavity from the graph that you see there. Okay. So the most of the problem that we're going to have is going to be following similar to this one, just like the when you looked at the increasing and decreasing function, there's not going to be any different, but you're just going to have to go, extend your differentiation to one more step, which is f double prime prime. Okay? The second derivative test is the one that we want to look at next. So here is the second we want to so we want to find a relative extrema. Okay, we're going to use the second derivative test. So if you want to do this using the first derivative test, then you're going to have to take the differentiate the given function. You're going to have to create a table like what we just did, and you want to find out which interval function is increasing and decreasing, and then you look at the arrow going up and down and down and up, and that's going to be your first derivative test. But as I mentioned, the second derivative test, we don't have to create a table or anything like that. And so what we're going to do here is we're just going to use the second derivative test, as I mentioned. So if you find that f double prime over c is going to be, greater than 0, then it's going to be relative minimum. It's going to be less than 0, then it's a relative maximum. So let's just take a look at this. I have f of x as a given function is minus 3x to the 5 and plus 5x cubed. I will show you the graph in a minute, but let's just assume that we don't know what this thing looks like. Okay. Now we're going to have to find the derivative of this function first. Okay? So let's just find the f prime of x. So then I have what? 15x to the 4th and plus 15x squared. Right? So if I take out the 15x squared as my common factor, then I have what? 1 minus x. I kind of switch the places. Okay. Now we're going to have to find the see if we can find the critical numbers from the f prime of x. So we're going to find the critical numbers. Why do we have to find the critical numbers? Because you want to find the relative extrema, and the relative extrema, you need to know what the critical numbers are. And in concavity tests, you need to find the points of inflection. But when you want to find the relative extrema, you have to find the critical numbers. So in this case, the f prime of x, the f of x is going to be polynomial function, so we're not going to have any x value that's going to be undefined. So that's going to be fine. But we're going to look at the critical numbers here. So you take the f prime of x. So Because we don't have any x value that makes this function as defined, we're just going to make that equal to 0. Right? So here it is. So f prime of x equal to 0. Then we have 15x squared times 1 minus x squared equal to 0. Why don't we just divide both sides by 0? So we're going to do this. X squared. So then we have what? 1 minus x squared equal to 0. So that means we have what? X squared equals to 1. Right? Now, the one thing, let me just go back here. This is not right. Kind of a messed up. We need to make this thing. I thought, that we have x squared. Oh, okay. I'm going to redo this because that's slow. Okay. There we go. So we have x squared there. We're going to have to, equate that. So we have what? 15x squared equal to 0. Then I have a 1 minus x squared equal to 0. So here the x has to be 0. Over here, you're going to get x squared equals to 1. So x has to be plus minus 1. So those are going to be my critical numbers. Now, what we are saying here is that these at these critical numbers over here, right? We're going to determine, whether it is a relative minimum or maximum by plugging these critical numbers back into the f double prime of x. Okay. So why don't we find the f double prime of x? All right. We're going to go back to the f prime of x before I put them into the nice vector format. Let's look at that. We're going to take another derivative of that one. So I have a minus 60 x to the cube, right? Then I have a plus 30x. Okay. All right. So we do have now the second derivative of the given function. Now, the second derivative test says you're going to have to plug in these critical numbers into this f double prime of x. And if the given f double prime of c is going to be greater than 0, it's going to be relative minimum, and so on. So, we have that already up there. So we're going to have to evaluate these three numbers here. So we're going to have evaluate f double prime of, for example, these critical numbers that we just found. So we're going to evaluate f double prime is at -1. And we're going to evaluate the f double prime at 1. And we are going to evaluate f double prime at 0. Okay. Let's plug it in. Now let's plug the -1. Oh. All right, let's just evaluate the x equals to -1. So we're just going to plug that into the function here. Let's do that. Minus 60 times -1 to the cube. and the plus 30 times to the negative 1. Right? So we have a positive, a positive 60, right? Minus 1 to the cube, you get negative 1. Negative 1 times a negative 60, we get positive 60. And 30 times minus 1, you get negative 30. So that's going to be a positive 30, which is greater than 0. So we know that this is going to be relative minimum. Now let's do the same thing for the x equals to 1. So you got minus 60 times the 1 to the cube and the plus 30 times 1. Now you have what? Minus 60 plus 30, which is the minus 30, and that's less than 0. So that's going to be your relative maximum. So as you can see that, if we plug in 0, let's find out what we get. We got minus 60 times 0 to the cube plus 30 times 0, well, you get 0. So in this case, this test failed. But, we pretty much, find out what the relative minimum and maximum was. So if I draw this function, this is the original function here, not f double prime, but the original f of x. Let me just draw this function. And you will have graph, something like this. Okay. And going up like this, coming down like that. So what we're seeing here is that over here, like that. Okay. So this is going to be a relative maximum. It happens at x equals 1. So if you go back and plug in x equals to 1, y becomes 2. So we got 1 and 2. So that becomes your relative maximum. And we found out that x equals to minus 1 over here is going to be relative minimum. And if you plug in minus 1 to the original function, you get y equals 2 minus 2. So that means you get a relative minimum. And this function that I just drew is the original function, f of x is equal to minus 3x to the fifth plus the 5x cubed. Now, it is not unusual that students get confused, among these different graphs. Okay. Now remember, when you find the relative minimum and maximum, when you find the relative extrema, we are finding the relative extrema on the original function f of x. All you find, the other things, stuff that you're finding, like f prime of x and f double prime of x, is just indicating on that original function f of x, where's the functions increasing and where the concavity is going up and down, and what the relative extrema on original function. Okay. So sometimes, I have a student, oh, I thought this was the f double prime of x graph. No, we always, we're always working on the original graph, finding increasing and decreasing function and finding relative extrema. You are using the tool f prime of x to find those information and the first derivative. Okay, on the original function. The same thing goes for the concavity. When you use the concavity test, you are using f double prime of x from the original function to find out whether concavity went up or M. Right? But we are not dealing with the actual graph of the f prime of x or f double prime of x. We are not doing that. We always want to go back to the original function and using these derivatives to give us information where the function is increasing and decreasing, where the relative minimum is, where the relative maximum is, where the function, the graph is, open up, open down, concavity. And if possible, then we can, instead of doing it using, first derivative test, we can use the second derivative test to find out where the relative maximum is. So as you can see that if you look at the third case over here, we found out that from second derivative test, it fails. That's right over here. And we don't know what's happening there, whether it's going to be a relative minimum or maximum. We cannot tell. Obviously, it's not neither, right? Because we know that what relative minimum is and relative maximum is. And when x equal to 0, it's just nothing. Okay? So what we have now here is the another applications of a derivative test. So we need to make sure that you understand the difference between the first derivative test and the second derivative test. Now, these both first and the second derivative test is testing for relative extrema. First derivative test, you have to go through the set up the table, find out which error goes up and which error goes down. That's the first derivative test to find out what the relative extrema is. Second derivative test, we are not doing that. We're just going to take the second derivative of the given function and then look at the conditions that, if the function f double prime is going to be greater than 0, then it's going to be relative minimum. If it's going to be f double prime is less than 0, then it's going to be relative maximum. If it's going to be equal to 0, then we don't know. So the difference between the first and the second derivative test is just a different way of approaching the conclusion. The first derivative test is always going to work, but it takes more time. If you want to use the second derivative test, it's not a shortcut. But if you if the f double prime of some constant is going to be equal to 0, then you don't know what's going on. You're going to have to go back to the first derivative. But that's kind of drawback. But majority of the time, most of the time that a second derivative test works. But in case that your test fails, then you just have to go back and do the first derivative. So I'm going to conclude the lesson here. I am trying to find out which online method is working best for you. We've been doing synchronous lectures on Mondays and Fridays, and we met on Wednesdays. So if we can somehow try different things to help you understand better, then I want to try that. So this is another way, because my plan was that since we are meeting on Wednesdays, then we don't really have to meet both days for the asynchronous lecture. So maybe we'll do one on the synchronous lectures on Mondays. We meet on Wednesdays, and I'll have an asynchronous lecture on Friday. So let's find out, see if you guys like it. Then if you do, then we'll do this for the rest of this. Okay. All right, guys. Thanks for make sure that you watch this, and there will be attendance. So the good way for you is to just send me an email saying that I watched your video on concavity, then that would be enough. Okay. So we'll talk about this a little bit more on class and see there's any questions, or I'll see if we can make it better for you. Okay. All right. So I'll see you guys in class next time. All right.